Okay, so we were working on energy methods. We began an introduction to energy methods in the last lecture. And, we did some very basic stuff in doing so. We defined things like forces and work. Force only does work when it moves through a displacement, and only the component of displacement in the direction of the force is actually contributing to work. All that stuff was stuff that was pretty much review, but nevertheless stuff that you had, it's good for you guys to view again in the context of this course. Herein we described something that I'm not sure you had seen before. Maybe you have, maybe you haven't, and that is the concept of strain energy. This is, again, just review from last lecture. Really what we would take is any structure that's under load that has stress. As you integrate from zero strain up to the strain, the magnitude of the stress destrain, what you're looking at is a stress-strain curve, top right here, where you're sweeping out for any level of strain. You have a certain level of stress. And if you integrate under this curve, you're essentially storing energy if this is elastic. That means if you were to unload it, if it comes back down the same path, then you are storing that energy. We're going to call that an internal recoverable stored energy. We're going to ultimately call it strain energy. So this is on a per unit volume. At any point, there's integral of stress destrain gives us strain energy density, U0. And then, of course, we can integrate U0 over the volume of the structure to get the total strain energy. So that was a pretty important concept that we covered last time. I think we have gone through and done that. For a linear elastic material, we know that stress is just modulus, Young's modulus times strain. And so because now this is a linear problem, this becomes much easier. The strain energy density is 1/2 E, the modulus times epsilon squared. So it goes as the strain squared. Note, you could also do a substitution and say that this is now functionally equal to 1/2 stress squared over the modulus. That's where we're substituting this, solving for strain and then substituting into this equation gives us then this equation. And another way that it could be expressed is just 1/2 strain times stress. Now, those are all functionally equivalent terms for a linear elastic material. Now, when one of the kind of final statements that I believe we made, correct me if I'm wrong, was that as we are applying a load and we get deformation, because there is deformation at the point of application of the load is doing work. And the work, then the energy associated with that work gets stored as energy under the curve. Okay, now that presents us with this idea that work and energy are related to each other. So the strain, if we're an elastic medium, the work due to the external load is then stored as strain energy in the bar. This assumes no dissipation, no plasticity, nothing like that, no friction. And in that case, what we have is a stored strain energy that is directly proportional to and effectively equal to the external work. Now, another way to express this, work was expressed in this way for that very simplistic uniaxial bar. Essentially, it was the force integrated over the displacement from some initial state to some final state. We can solve that equation for force, and we can then say that in this case, it was a point force, so we're going to call it P. So P is equal to the partial derivative of the strain energy with respect to the displacement at the point of application of load. The force is equal to the partial derivative of the strain energy with respect to the displacement at the point of application of load. Now that's kind of a neat little phenomenon, actually. A guy named Castigliano was the one who formulated it in this way. This was all the way back in 1879. This particular equation or form of an equation is really, it's the concept that you can find the force by differentiating the strain energy with respect to the displacement. This is called Castigliano's first theorem. Now we're going to use that in an example here shortly, but before we do that, I want to introduce you to another concept. That is the concept, and please let me know if I'm going too fast. That is the concept of complementary energy. Now, if you remember, and I'm going to go back a slide or two, so hold your thought. I'm going to come back to this, so don't panic that I'm leaving it already. What we saw here was that strain energy density was the integral of stress d-strain, and we saw it as the area under the curve. Now we can flip stress and strain and write it in such a way that strain is now a function of stress, and then the area under that curve is functionally equal to this area that I'm highlighting here. And I'm going to call that U sub 0 C, the complementary energy. So this is the energy complement to the strain energy. All right, so now that we've seen that figure, let me go to the equations. So what I said was we integrate the strain over the stress, and that gives, from some initial state, zero strain state, up to a stress state, that gives us a complementary energy. This is a per unit volume complementary strain energy density, which then we can integrate over the volume to get the total complementary energy. Now, this is in some ways a different energy than what we had before. That is, if we know that this is a non-linear elastic, this area and this area are not the same. However, it turns out if this is a linear elastic medium, then this area and this area are the same. Okay, now that's an interesting point to make, but that doesn't really describe for us this other concept that is much like we said that we can calculate P as being the derivative of UC with respect to the displacement. The point, we could calculate the force by taking the, not UC, I'm sorry, U. We can take, let me write it again here. So P, this is, the first form was P is equal to du dy. Now we can also show that we can express the displacement as being equal to the partial derivative of the complementary strain energy with respect to the applied load. So here we have really two equations. The one that I've written in yellow and is boxed, that was Castigliano's first theorem, which was on the other slide. The one that I am now circling, which was previously typed into the slide, this is what's known as Castigliano's second theorem. Again, this was derived, about 150 years ago and has been used since. It's a very powerful mechanism for computing things like displacement or load, and we'll see how useful it is in a few slides. All right, so are you guys still with me? Unfortunately, my monitoring computer where I can see your faces and see my own screen reflected back to see what you're seeing, for some reason it has not been updating over the last couple of days, so I'm not seeing your faces as well as usual. If I'm not responding to something in the chat window or something, if you're waving at me and I'm not paying attention, please turn on your mic and just speak your questions. Looking at the chat window now, I do see that Aiden has asked a question. Is the complementary energy just unrecoverable energy from strain, or what is the physical meaning of it? So that's a great question. Garrett, I'm not sure what was your response to Aiden. I think maybe you intended that. So what is the complementary energy? So in this case, let me go ahead and get it on a chalkboard here. Okay, if I have strain and I have stress, and I'm going to draw this generic nonlinear curve. Okay, and I'm going to draw the horizontal. So we call this U0C, the complementary energy, and we call this U0, the strain energy. Now the key here is if this is elastic, the recoverability of either one of these energies is dependent on this being an elastic problem. What does that mean? That means if I load up this curve and unload, I come back down the same path. Oh, thanks, Garrett. I see your second comment there. So if we load up and we come back down the same path, then we have recovered the energy. Okay, now in that sense, we could functionally recover either the complementary energy or the strain energy. Now, in terms of how much energy is stored to actually do work, really it's the internal strain energy that can be converted into things like kinetic energy. So if you have a nonlinear response on, say, a bow and arrow or a crossbow, the amount of energy that would be converted into kinetic energy is the area under this curve, that is the strain energy, and the complementary energy does not have a direct analog to that. So really what the complementary energy allows us to do is use Castigliano's theorem, and you're going to see an example of that in a few minutes. So I hope that answers the question. If not, hit again in the chat window. So I mentioned this and I kind of drew it already, but for a linear elastic material, this curve is linear, so the areas are functionally the same. So U and UC are the same, and we don't need to worry about distinguishing between them too much. Although in practice, you probably should try to be rigorous about differentiating them whenever you can, just so you don't get yourself into trouble when you have something that would be a non-linear elastic material. By the way, before we move too far, I'll just make a comment here that if we have whether it be linear or non-linear, it doesn't really matter, but if we have a non-elastic material, where if we unload and we come down a different path, this would be a typical path. So I'm going up this way, up until yield, and then coming back down here. This is strain and stress. Actually, the area under the curve, because the total area under the curve would kind of come down to here, but a big portion of that's this portion of the energy is no longer recoverable to do elastic work. Only a portion of that would be energy available to do some other type of work. So what's going on over in this region with the horizontal lines is actually at the sort of atomistic or more at the grain boundary level, what we're getting is dissipation of energy as you're doing maybe phase transformations or slip planes are occurring. You're moving atoms past each other in a way that's not recoverable. So that's energy going into the material, largely becoming heat, and there would be some elastic energy still available. But you have to be really careful when you're talking about strain energy in the context of materials that have done gone into the plastic zone because you don't get all the energy back. Okay, so coming back from that little tangent, let's now do some example of what's called Castigliano's method. So in summary of the two equations that Castigliano wrote, Castigliano's first was that a force, now this is a generalized force, could be a moment or something else, a force can be determined if you can write the strain energy and then take a derivative of that strain energy with respect to the displacement. Displacement here also generalized, so it could be an angle at the point of application of the load. And this really needs to be thought of in a vector sense. So in the direction of applied loading, you take a derivative with respect to that direction, you're going to get a force with respect to that direction. Similarly, Castigliano's second, again, generalized, this could be a displacement or an angle is equal to the partial derivative of the complementary energy with respect to the applied load. So Pi and delta I represent these generalized loads and displacements. They could be torques, they could be angles, but in a vector sense. These theorems really are useful for convenient, I like the wording, I kind of like this myself, conveniently finding the deflection, or alternatively, conveniently finding the reaction at a single point of interest, really. It's rare that you're going to try and find the complete deflection using Castigliano's method. You might. It's possible, but usually if you're only interested in a few points. Now, let's do an example. Here's a cantilever beam. This is quite similar. We've done this problem before. We did it using elasticity theory. We did it using beam theory. Now we're using Castigliano's theorem to calculate the deflection of this structure. So look first just at the beam itself, the top portion of this figure. We've got a point load. On the left-hand side, we've got a constraint, so it is cantilevered out. The question, of course, is then how do you calculate the tip deflection? Now, you guys probably remember, we know the beam bending equations, and you could write, the fourth order differential equation. You could integrate up and use appropriate boundary conditions to get rid of the integration constants and ultimately calculate the deflections that way. It's a very good, simple method to do it, simple for these problems. A little bit harder in some problems. But let's now approach this from a little bit of a different way. Let's use Castigliano's theorem. Okay, the first theorem, actually we're going to start with the second theorem. Castigliano's theorem is, going back to my equation, we're trying to find the deflection at the tip. So we're using the second theorem, that's the complementary energy. So in order to calculate the complementary energy, we integrate the strain over the stress. So this portion here is the complementary energy density, and then integrated over the volume, so from one end of the beam to the other. So this is a pointwise quantity and then integrated over the volume. Now, what is complementary energy? Well, for a linear elastic material, it's easy enough. The relationship is just a linear relationship, and it comes from E epsilon is equal to sigma. So we can solve that equation for epsilon. And so I've plugged this in. So sigma over E is now, so we're integrating sigma over E d sigma, which obviously becomes sigma squared over 2E. And then you integrate that over the volume. So really the volume integral becomes an area integral and a length integral. So dA dz. All right, I am watching the chat window. If you have questions, go ahead and pop them in there, please. Now, recall from our beam bending lecture that we can actually calculate the stress in a beam pretty easily if we can write the moment. Okay, so here is the relationship for this, essentially one-dimensional beam with an unspecified cross-section. We're going to say it has a cross-section that gives us an area moment of inertia I. Obviously, it's got a centroid And hold on just one second. I have a child coming into the room. Hey, Andrew, I'm in lecture, bud. Okay. Sorry about that. Anyway, so if I write this form that relates the bending moment to the stress, so now we have as a function of position, so y is position within the cross section, and along the z-axis, the moment gives us a relationship between position because it's dependent on z. So now we have a positionally dependent stress, which we can then plug into the stress value that we saw on the prior slide. So now our complementary energy becomes an integral over the volume of 1 over 2e, where we can write the moment of z times y over I, square that term dv. Pretty simple. Now, it's worth noting that the moment itself is constant with respect to the cross-section. Recall the moment was a moment resultant over the cross-section. So we can actually pull that outside of the area integral. Recall I said that the volume integral was then an integral over an area and along the length. So we can pull the moment outside of the area integral, and then we can do this integral first and then do the remaining integral with respect to dz. Now this form here is something you've seen before. The integral of y squared dA is what? Well, it's pretty easily recognizable as being the value I, the area moment of inertia. So here we put an area moment of inertia here. That effectively cancels one of the areas of moments of inertia there, and our new form of the equation becomes the total complementary energy in the system is the integral over the length of 1/2 the moment squared over EI dz. Now, this is actually a pretty important equation for a structural engineer who does a lot of beam theory. You should sort of tattoo this on your brain, memorize it. You're going to use it a million times. It's not a hard equation to remember, once it comes right down to it. And then ultimately, you would not have to rederive this equation if you were doing an exam or a homework set or similar, and I said, well, calculate the complementary energy in a beam. You largely could write it this way, although if the area is not constant over the length, you'd have to be a little bit careful and break it up into the sections where it might be piecewise constant and similar. Anyway, so there we go. There's our complementary energy in the beam. Now it's a function of moment. Of course, we still need to now know what that moment is, and we'll get back to that in a minute. Let me know if I'm moving too fast. I'm not seeing any questions coming across, so I'm going to keep moving ahead. So that, as I mentioned, is complementary for bending about one axis. You don't need to rederive it if the appropriate assumptions apply. You could add another term if you had bending about two axes. Not terribly complex. Okay, so from Castigliano's theorem, we know that delta P, this is the displacement at that point of the applied load, is equal to d by dp of the complementary energy, which is a function of P. So this here is not UC times P, it's actually UC as a function of P, where UC of P is equal to this equation. So now, the moment is then a function of P. So, theoretically, we could put this would be, M is a function of Z and P there. Nicole's asking me to go back a slide. Here you go, Nicole. Give you a second to copy anything you may have missed, and then if you're not able to copy it before moving forward, then we can come back to it after lecture. Okay, so There it is. Complementary energy. Castigliano's theorem is laid out. We're ready to go. So this solution can be most simply expressed as this. For some reason, I got a typo. This would be delta, not capital delta, lowercase Greek delta, is equal to partial UC partial P of the integral of. So here what I'm doing is I'm using what amounts to chain rule, I guess, to say that the derivative of m, the derivative of the integral of m squared dz, the derivative of that with respect to p can be then expressed as mz times the derivative of m dp, and then all of that integrated. So this form here is probably the simplest form. You always should sort of start with that form when you're doing these, because it'll make the math a little bit easier when you do it. But if you do it the other way, if you square the moment first and then take derivative, that's fine too. You'll get the right answer as long as you do it correctly. It's just more opportunity for algebraic error. So this is a good form to put it in. So this is going to be one of those circumstances where I say do as I say, not as I do. In the example, I will actually go ahead and square it first and then take the derivative, because for this one it's so simple. I just squared it and did it. For the harder derivations, it tends to be a little harder. I know I'm kind of moving a little fast through these slides. I'm happy to come back later if we need to. Okay, so here I have now made a substitution. I say that the moment, if I take a free body diagram, now we're looking at the bottom half of this diagram. If I take a free body cut somewhere in the structure, I know that I have still the point force at the tip. I have a reaction force, a resultant force really, at the boundary of my free body diagram. This is a shear value on the face, and of course I have a reaction moment there as well. Resultant moment really is what's better described as. And so the totality of this moment is going to be equal to the distance from P to the point where the cut is made. So that's L minus Z times the magnitude of the force P. So M of Z is just L minus Z times P. And then I'm plugging that in here. You recall this was the integral of m squared dz. So I've made my substitution. I have L minus Z squared, that's this term squared, times P squared, that's this term squared, dz. And of course, I can easily expand the L minus Z squared. So I get L squared minus 2LZ plus Z squared. And then I can integrate that over the domain. The domain in this case is from 0 to L, the whole length of the beam. And so after I do the integration, I get L squared Z minus LZ squared plus Z cubed over 3. And I apply the limits of L and 0, and I get that the total complementary energy in the beam is L cubed P over 6EI. Okay, I hope you'll see that that was relatively easy to do. Now, the next thing we can do, of course, is apply Castigliano's theorem. We're going to take the derivative of this term with respect to P. So that's coming on the next slide. So here it is. The displacement P is equal to d by dP of L cubed P squared over 6EI. We actually apply the derivative. We pull down the 2, which cancels a portion of the 6. So we end up with L cubed P over 3EI. This is our tip displacement. So this is the displacement at the point of application of the load. Note this is the only place we've computed the displacement, because in Castigliano's theorem, we're only computing it at the point of application of the load. And we get PL cubed over 3EI. And oh, by the way, as you might have guessed, this is identical to the tip displacement that was predicted by beam theory. I think when we talked about beam theory, I said memorize this equation, it's going to come up again. Here it's come up again. We recover that exact solution that would have been predicted by beam theory, and we did it using instead Castigliano's method. Okay, now that is, I think, quite useful. It's interesting. So you might ask, a natural question perhaps is, well, Dr. G, if you can compute it using beam theory, why would you want to do it this way? And the answer to that question is many times these things are not constants. Your cross-sectional area isn't constant, your thickness isn't constant, your area moment of inertia isn't constant, things like that. And it turns out that often when you're integrating up rather than integration is harder than differentiation. And although you needed to do some integration in this equation, you needed to do less. And oh, by the way, you note that I wasn't calling for any boundary conditions in this description. The boundary conditions sort of took care of themselves along the way. Hence, because of those two things, we don't have to worry quite as much about the boundary conditions, and we're differentiating rather than integrating. This is easier. And, you may not need the displacement everywhere along the beam. If you're interested, if you're, Burt Rutan, and you want to know whether the Voyager is going to have a wingtip strike as it rolls down the runway, and it did. If you wanted to avoid that and you wanted to estimate what the tip deflection was, because that's the first place that's going to hit the runway, you could use this method to sort of fairly quickly estimate whether that would occur. Now, the next question is, well, what if we want to know, Dr. G, I know you're applying this tip force at the end, but what if I actually want to know what the tip force, or I should say what the displacement is at some other point, like the midpoint? We're going to do this midpoint example. And my response would be to, well, go right ahead. You can do that calculation too. It's not hard. Now we know that the point force P is actually an applied load, but we can imagine another load to be present. In this case, I'll call it an imaginary load, although this is not imaginary numbers. This is imagined as in we are pretending it's there. So here we have a point load applied at the place of interest. I want to know the midpoint deflection of the beam. So I will assume that I have a load there, calculate the midpoint deflection, and then, I have my answer. And I can do that even using Castigliano's theorem. Why? Well, I do know that the deflection at the point of application of the load, in this case Q, is going to be equal to d by dq of the complementary energy. Now, this problem is very similar to the last one. It's not hard. The difference here is that we have much like I said, well, you might have to keep track of different areas. Here I'm going to say we're actually going to keep track of, we're going to do our two different integrals because the moment changes as a function of position from one side to the other. So sometimes you're going to have to track these things a little bit differently. In this case, the total complementary energy has two parts. One is what we'll call region 1 of the beam. That's from 0 to L over 2. The other is in the other region of the beam. That's region 2. We're going to say from L over 2 to the end. And so I can say the total complementary energy is just the sum of those two energies. The first one is the integral from 0 to L over 2 of M, in this case M1. And U2 is the integral from L over 2 to the end of its moment, that is M2. In each case, those moments squared over 2EI dz. Now note, I can just go right ahead and jump to this scenario where I happen to know that the area is constant for the beam. And the moments of inertia, area moments of inertia are constant, as well as the material properties, E. Okay, now this becomes just a problem of, can I write the moment? The answer is, of course, yes, I can. This term here, L minus Z times P, that was the moment that we used in our prior calculation. Okay, really that is from, I'll go ahead and delete this and say from this diagram, L minus Z is the distance from here to here times P is the moment. You do have to be careful about the signs on these. So, make your appropriate sign assumptions and state them and keep track of sign very carefully. The other moment, now we're taking a cut that includes, this free body diagram now includes this imagined force Q. And so now what we have is actually two contributions to the moment, one from P, that one is actually unchanged, but now we also have one from Q, and the moment arm on that location is from here to here, that is L over 2 minus Z. So it's no longer L minus Z, this one is at L over 2 minus Z. And so the moment contribution in that region actually has these two components, the portion associated with Q and the portion associated with P. Now, outside of that, really, there's no difference in what we're doing. I plug, oh, I did that one incorrectly. So this one goes up here, and this one goes up here. And then, we do the math, and I would sort of encourage you to just trust that I have done this correctly and maybe get to the end equation. If you're going to copy one, maybe only copy the end. It's a lot of writing to get the intermediate steps. But please do trust that I did it correctly. We take that moment, we plug it in. So here's the moment squared over 2EI for region 1. Here's the moment squared over 2EI for region 2. Note, for some reason, I pulled the P squared out the back side. That is a constant. I don't know why. I should move that to the front side rather than the back side. But, it is a constant, so it can be moved outside the integral. And then, of course, this is just the same expression wrapped in parentheses. And I'm going to say now I take the derivative of this above expression. It's the same expression with respect to Q. And when I do that, what I get is d by dq of this. So this term now in parentheses was the result of completing the integrals here. I still have the derivative present. And then when I apply the derivative, what I get is the following. That is 2L cubed Q plus 5L cubed P over 48EI. Note we're taking the derivative with respect to Q because Q is at the point of interest where we are trying to calculate the deflection. Okay, I guess I don't really complete this in the strictest sense, this example. So now you ask me, okay, well, Dr. G, what is the actual deflection then? Well, in this scenario where I've put an imaginary load, so I have the actual load P and I have this imaginary load Q, we know that even though I've drawn it there, its magnitude is 0. So then I just apply this is equal to 0 here, and the actual displacement at that point ends up being 5 L cubed P over 48 EI. So very simplistic calculation, gets us the deflection at the point of interest. You can generalize this actually to say, well, I can calculate it anywhere in the beam just by modifying where I assume the integral begins and ends for each of these two components of energy, complementary energy. Okay, any questions on that?
Why is Q equal to 0?
Yeah, so that's because this is this hypothetical scenario where I want to understand what the deflection is at the midpoint due to a load at the tip. Okay, and this comes up actually relatively frequently. Don't assume that this is a totally hypothetical, never to happen scenario. In fact, it's quite common that we know the load is going to be applied at one point, but we want to know the deflection elsewhere. So in that sense, I want to know it here. To use Castigliano's method, I need to take a derivative with respect to a load at that point. So in order to know what the complementary, in the end, what we have is UC, which is going to be a function of Q. So we need to take the derivative of that, d by dq of UC of Q. That's what we're doing. In order to do that, we actually need to calculate the imagined complementary energy that would be there. But then since there is actually no point load there, we could then set it equal to 0 at the end. However, if we set it equal to 0 earlier than that, before we took the derivative, we wouldn't have, in fact, let me go back here. You recall this equation. So if we set it to 0 at the beginning, then the total energy, total complementary energy would have been this. P squared L cubed over 6EI. If we took the derivative of this term with respect to Q, we would get 0. Now, of course, we know that the midpoint deflection is not 0, so we actually need to compute the energy associated with Q before setting it equal to 0. Okay, so Nicole asked, can you explain the moment arm from the bottom picture again? So yeah, I can surely do that. No, that's not going to be helpful. Here, we're looking now at this scenario. So, the moment arm to P, so P is at the position L. So out here is L. The distance from here to here is L minus Z. So the moment arm for P will be L minus Z. We know that Q is at the position L over 2. So now the moment arm to Q is L over 2 minus Z. So very straightforward, Nicole. Okay, any other questions out there? All right, we'll keep on chugging here. Now we're going to do one more example with Castigliano. This is going to be for what's called a statically indeterminate system. Here's an example. Very simple. This is not going to be as simple as the other one, but nevertheless, it's a simple example. So let's imagine that we have a uniaxial load-bearing member. So this is just a bar with a point force at the end. It is constrained on the left edge. We've got cross-sectional properties E and A, which are constant in the beam from one side to the other. Now, we can imagine that scenario where there's no spring attached, and then we know we can very easily compute the tip displacement. But then what happens if we add a spring at the end? So now there's additional stored energy that's going to be present in the spring. And so the way I'm drawing this is just a spring is going to be attached to another rigid body over here. And so, any deflection of the tip of that axial load carrying member is then going to be also a deflection that the spring is carrying. So here we can calculate the total complementary energy. Now, if you recall, I said to memorize an equation here. So that was the integral of m squared over 2EI. So this was the beam bending energy, complementary energy, not strain energy, but complementary energy, m squared over 2EI. That was for bending. There's an analogous complementary energy for an axial load carrying member, and it takes a very similar form. So you get a generalized force. In beam bending, it was M. In axial load, it's the force itself, force carried through the bar, divided by a generalized stiffness. So in bending, it was EI. In the axial load, it is going to be EA. Okay, of course, we still get this constant 1/2 in each case. So this equation, without deriving it, you can basically say, yeah, I get it. This is strain energy for a constant force carried through an axially loaded member. The complementary energy is going to be F squared over 2EA integrated over the length. Now, there's also going to be energy stored in the spring. And this is, so if you think about spring energy, you're going to have 1/2 kx squared is the spring potential energy. That is the strain energy density, really, of the spring, called the spring energy. It has an analogous complementary energy that takes, again, this form here. So it's a generalized force over a generalized stiffness. So force through the spring squared over 2K. There's no integral here because it's a discrete spring, but we have the spring stiffness in the bottom. We have the force in the top. So you should sort of memorize these forms, the spring form, the axial extension form, and the bending form. Anyway, so this is the total complementary energy in the system. We do need to differentiate the force carried by the bar from the force carried by the spring. And so, you can just basically do a free body diagram on a point here at the end. So here's the point force, and then the spring we're going to assume is adding in a positive direction. We're going to assume that there's a force from the spring, and then both of those forces would be carried through the bar. This helps to differentiate the fact that the point force is not all carried by the bar, nor is it all carried by the spring. This is a force balance at the point of application of the external force P, and therefore it helps us to establish how much is carried through the bar and how much is carried through the spring. So if we then plug that into our complementary energy equation, I've just made this a little substitution here. UC is equal to L over 2EA times P plus Fs squared plus Fs squared over 2K. Complementary energy, pretty easy to calculate. Now, since P is the applied force, we're going to take derivatives with respect to it. Now, one thing that we can do is we can sort of cancel out the spring force and put it in terms of the spring stiffness and write it this way. So this is one way to do it. We don't have to do it this way, but this sort of takes care of making it so that the spring force is tracked as energy within the spring. So now the total complementary energy is equal to P minus delta K squared plus delta squared K over 2. This is kind of a little bit, I don't want to say cheating. This is perfectly legal because the spring itself is linear, and we're saying that, so for the deflection delta with whatever force, the complementary energy and the strain energy in the spring are the same for a linear spring. So now we'd have to be more careful with that if it was a nonlinear spring, but this works here. Okay, then what we can do, of course, is we can take the derivative. We're taking the derivative with respect to P. And what we get is that delta is equal to L times P minus delta K over EA. Note we still have a delta on the right-hand side, so we ultimately need to solve for the delta, and what we get is this. Delta is equal to LP over EA plus KL. Now, is that meaningful to us? Well, we need to think about that a little bit. Certainly, we have calculated a deflection due to the applied force. This was a statically indeterminate system, meaning you couldn't calculate the force without applying some sort of additional condition. The condition was the spring deflection and the force balance between the two bars, or I should say between the bar and the spring. So it's like a compatibility equation almost. So we have proven that we can do it. Did we get it right? That becomes the next question. How correct is this calculation? And so we need to do some sanity checks on this. Or at least I would argue you should. And so thinking about, anybody want to suggest a sanity check? While you guys are thinking about a sanity check, I'm gonna jump over and answer the questions in the chat window. So David asks, is delta K one or two variables? It is one variable. It's one variable. Hannah asked, is there a reason to use capital delta instead of lowercase for this one? I guess not particularly, no. Anybody have a sanity check yet? So I'm not hearing any sanity checks. So Ethan says, thanks, Ethan. You say delta should probably not be greater than the length of the beam. Okay, so that's a good sanity check, but that actually wouldn't necessarily apply here. So let me go. This schematic diagram, this physically could be anywhere. It could be some really large distance over here. And so theoretically, you could stretch the original length to be 2 times the length. Where does that go bad? That becomes problematic if you get into nonlinear strength. For metal bars, you certainly couldn't stretch something 2x and still have it remain linear. So your point is well taken and good. But if it were a linear system, and you made the assumption of small strains, there's really nothing physically wrong with it going a full L, but I don't think that really has practical meaning. It's more of a theoretical discussion. There's another sanity check that I would suggest, and that is, in fact, we kind of alluded to it already. If I go back to this diagram, well, let's do just a quick calculation of what happened if we took the spring away, meaning if we took the spring and set its stiffness to 0. So if K is equal to 0, do we recover what we know to be a reasonable calculation for displacement? So this now just becomes an axial bar. If I look at the answer that I've predicted, delta is equal to PL over EA plus 0. So PL over EA, that is absolutely the axial bar, change of length for a constant cross-section, constant material axial bar, linear elastic bar. So that is a nice little sanity check. We could, of course, do the opposite sanity check, and that's to say, well, what if we took the bar away and then only applied the spring? That's kind of like saying E is equal to 0 rather than K. And so if we go down and we check this, so again, setting E equal to 0, then you get PL over KL, so you cancel the L's, and you get P over K, and then that just becomes the deflection associated with a spring. So that checks out. So both of those limits check out, and we can have fairly high confidence that this answer is correct. Nicole had volunteered one. Thanks, Nicole. So you said would displacements at the end be 0 because it's cantilevered? So we got to be a little careful with the use of that word cantilevered. Cantilevered really refers mostly to beam bending problems and the boundary conditions associated with bending. So that is the displacement at one end is 0, the slope at that same end is 0. I'm not sure which end you're referring to in your comment in the chat window. So the displacement at this end will be 0 because it is fixed at that end. I would avoid calling it cantilever just because this is not a bending problem, although you probably would have communicated your intent just fine and it would have been understood, no problem. But anyway, so it wasn't clear whether you might have been referring to this end, and so the displacement at this point would not be zero, obviously because we're applying the load there, and everything in the world is deformable at some level. You're going to get some deflection there. I think you were referring to this other end, though. Keep in mind that Castigliano's method only allows us to calculate the displacement at the point of application of the load. So we don't actually know anything about the deflection anywhere else in the beam, except maybe to Nicole's point, that's the boundary condition. We can make a statement of it. But you actually see that the boundary condition doesn't really show up in this equation. Other than it was probably necessary to actually get these complementary energies in their very lowest level derivation. But we kind of skipped that lowest level derivation because we know what the axial complementary energy is in a bar. So we could have also, getting back to this idea of I substituted in delta K for our spring force, we could have instead taken the partial derivative with respect to the spring force and then ultimately set that equal to 0, and that would have recovered the compatibility equation. That's the force equilibrium, the balance of forces at that point. But that's, I think, a little bit less interesting here. Okay, so any more questions about Castigliano's method? So obviously we've done some relatively simple examples of Castigliano's. Probably going to get a homework set where it's going to be a little bit more complicated than that, but that'll give you something to really practice on. That'll take more than a few minutes, but less than a few hours, hopefully. Something that would be viable for a test question. So look out for that. We're going to have that homework set going forward. All right. Now we have about 10 minutes, actually 11 minutes left in class. I want to start the next topic because I don't want to lose this critical 10 minutes with so little lecture time left. However, it's going to be a little bit pressing that we're going to kind of squish this over 2 lectures then. So, we might do a little review next time. This next really critical topic is this idea of virtual work. Okay, by sort of show of hands with the few that I can see, who's heard of virtual work before? So I'm only seeing 4 faces on the screen at this exact moment, and I got one positive response. So it sounds like most of you probably haven't heard of virtual work. Let me take you back to the beginning of last lecture, or I should say middle of last lecture. Really, it's the beginning of this lecture. David says when he raised his hand, he heard about it last lecture. Okay, so there you go. Maybe none of you have heard of it then before this class. Anyway, so recall our definition of a potential function. So a potential function was a function that related a force-like quantity to some gradient-like quantity. Okay, it was the derivative of some potential function with respect to the coordinate direction gave us a force. So if we can express something in this form, we can call that a potential. Now, what we could do is we could say, I'm going to define a potential function that describes the relationship to the external forces acting through external displacements. Now, what do I mean by that? So we're going to start to use this delta symbol. Really, we're going to eventually call this the variational symbol or the variational operator, but you can think of this for the time being as if we have a small increment of displacement at any point, really at any force level, a small increment of displacement at that point, we're going to have an increment of a potential function. So we're going to change the amount of work associated with this derivative, this small change in displacement. So we're going to say the left-hand side is the work potential function of the external work. We're going to put a minus sign in front of it to be consistent with this convention. And we therefore are defining a work potential. Excuse me. Now, similarly, we can say that we know there is a strain energy stored in the system. And if we take that same little increment of displacement at a point, we're going to have a corresponding little increment of strain. And you can in some ways think of that, so we're changing the internal energy. And we know that because internal energy is dependent on work, we're going to now start to call this an internal work. So it's an increment of internal work. This really is the incremental forces acting through incremental strains within the body. So now we have an external work potential, we have an internal work potential. And we can now examine what we're going to call a work equation, such that we have a total amount of work, which is the sum of the external work increments plus the internal work increments. And we know that these things balance each other out, so the sum of external and internal work increments need to be equal to 0. We call this equation virtual work. I got to deal with the idea of virtual work as opposed to real work, and I'll come back to that in just a minute. But I will mention that this idea of this work equation, since we derive these from an external work potential increment and an internal strain energy increment, this is functionally can be also written in these two forms. So du plus dv is equal to 0, or equivalently du is equal to dwe, where we recognize that the work, external work, and the potential of that external work had a negative sign in front of it. So these are all three different ways now of writing the same equation, and I'm going to call this the virtual work equation. Okay, now what exactly is meant by the term virtual in this context? It's not a virtual world, it is virtual work. Here, what I've got now is a set of definitions. So delta W, you might see it called delta, capital delta W in places. You know, it depends on what reference you're using. Doesn't really matter. It's just the symbology. This is work, virtual work. It's the work done by a force. So you've got at some point a force, and this is a generalized force, so it could include a moment, due to a virtual displacement. Okay, at that point, we're imagining a small increment of displacement to occur. And if there's a force there and a small increment of displacement, we have got an increment of work. Now that begs us absolutely begs us to define what we mean by virtual displacement. So virtually, a virtual displacement is any kinematically admissible displacement. So at this point, we don't need to know exactly what the displacement is. We just need to know it doesn't violate any boundary conditions. And it's a small increment of displacement. So it could be of magnitude 1, it could be 0.1, it could be 1,000,000. Doesn't really matter what the magnitude is. At that given point, we have that small increment of work done. And we have, because we have a force acting through this imagined, pretend, if you will, displacement field. So kinematically admissible, that means it doesn't violate kinematic boundary conditions. So, you know, getting back to Nicole's point earlier, if we had this axial load carrying member, we can imagine there being a small increment of displacement occurring at this end. It could move an amount delta U here. However, at this end, we know that this end is constrained, so we know that we can't have any virtual displacement that's non-zero occur there, because that would violate a boundary condition. So here at the left side, delta U is going to be equal to 0. Basically, we cannot imagine a virtual displacement field occurring there. We can at the right-hand side. So that's what I mean by a virtual displacement and a kinematic boundary condition. Now, as I mentioned, this displacement is arbitrary. This idea of it being arbitrary is so important. I'm going to circle it in big, big circles 10 times. Okay? It is arbitrary. We don't know what its magnitude is. We're just, we can imagine that an increment of displacement has occurred. So this is kind of a parenthetical displacement. It doesn't need to be related, at least in magnitude, to any of the actual displacements that result from the applied loads. Okay, David, I see your chat window question. What's the definition of kinematically admissible? Obviously, I've placed that up here since I think you asked the question. So if you still are confused, let me know. Okay. Now, so what we've imagined is this scenario where we have some applied force and we imagine some little increment of displacement to occur. If you can kind of massage your mind to imagine an arbitrary displacement field occurring there, then I'm just going to ask you to stretch it just a little bit further and say, okay, well, let's imagine instead at the displacement that occurs a virtual force, so a small little increment in force. This is the top result. Oops, apparently Google thought I asked it a question. Sorry about that. Anyway, so this small increment in force, analogous to a small increment in displacement, we're going to call that a virtual force. This would be any force field, potentially could be anywhere in the body, although typically we often are going to be doing it at external boundaries. It's not required, but it's commonly done that way. Any force field that is 0 on the boundary. Now, what do I mean? I think I actually misspoke there ever so slightly. This virtual force, so here I've got this axial load-carrying member. The virtual force, we can't violate any force boundary conditions. So if I apply a force here called P, I can't then have, if I imagine a delta force here, it's got to be equal to 0 in order to not have any violation of the boundary condition there. But somewhere internal, I can imagine that I've got an additional increment of force that's present there. So this virtual force, if we have strain at this point, and therefore we have I want to be careful with my displacement symbol. I'll call that, let's say, U. So if I have strain at this point and I have displacement at this point, then this virtual force does an increment of virtual work that is delta F times U. All right, so a virtual force is similar to a virtual displacement. It just has a different sort of boundary interpretation. Again, like we said with the virtual displacement, the virtual force is arbitrary. It need not be related to the actual force. And by the way, this is a generalized force, so it could be a moment, virtual moment. It could be a virtual stress, anything that can be generalized as a force. All right, now the final statement here this is the really important one, and we're going to wrap up after this. And then, I want you to write these words down, put them under your pillow, and absorb them through osmosis between now and Thursday, because this is a really critical principle. That is the principle of virtual work. A system, any system, structural system, is in static equilibrium if and only if the virtual work is 0 for all independent virtual displacements, or for that matter, virtual forces. So this equation, delta W is equal to 0, is actually a really critical analysis tool. This statement and this idea of the virtual force and the virtual displacement, these are profound ideas, actually exceptionally exciting ideas once you wrap your brain around them and understand them. These are the tools that allow us to do advanced structural mechanics in the finite element method. Okay, this enables the finite element method for reasons which you will see when we come back next time. We're going to do some calculations. We're going to use virtual work and this idea that there is some displacement field that is arbitrarily different than the real one that could exist. And we're going to use that arbitrary displacement field to find the real displacement field. Boy, that's such a powerful and exciting technique. And honestly, it's a little hard to comprehend at first. So, you know, it's between now and next lecture that's on Thursday. Chew on this for a while. Call me in office hours. Ask me questions. You know, this is a really important topic. Okay, so we're going to wrap up there for today. I'll hang on the line for a little while for questions. I did have one student ask for some office hours right here after class. So, you know, for that student, please also hang around. Don't forget that we had agreed to do it. You know, I think Nicole had maybe one or two questions as well. I don't know if you got that stuff copied. I'm happy to go back into those slides if you need those still. Other than that, I look forward to seeing you guys on Thursday. Have a good day.